make wind energy more economical and more accessible in the future. And some of them instead are working on automotive problems. We have a project with Volvo about electric trucks, and also we're doing something theoretical about the safety of cooperative autonomous vehicles. So I myself has not been living in the Netherlands always. So I was born in Trieste, in Italy, which is this green dot that you see there, which is quite a cold and windy city for being in Italy. That went working in the steelmaking sector for several years, and finally came back to academia in Delft, where I'm now indeed working on fault tolerance. So let us try to look in the question of today. So why uncertainty has a dual role in safety and resilience? So safety and resilience. There are several examples of where it makes sense to apply this. So I guess you know them. So I will not go too much into details. But I will have now a closer look of the kind of systems I'm considering, which I guess is the system that you are also considering, cyber-physical systems, where we have a physical plant connected to sensor and actuators, and we have some kind of network connecting these to a controller. So it doesn't need to be a wide area network, it can be the CAN network, the CAN bus of a car. And our goal is to make such systems safe and resilient against faults and degradation, which are physical things that can happen fast or slow, but also we want to guarantee security against attacks. And the reason is, if we have a loss of security in this layer, the cyber one, this can lead to problems with safety at the physical level. So we are looking at faults, we're looking at attacks at the cyber level, and faults, physical anomalies in the physical level. So one way that I'm using to get safety and resiliency as a final goal is to detect anomalies and then accommodate them. So I'm not a computer scientist. I'm not building encryption into things. I'm not making things more difficult to hack, but I'm a control system engineer. So I assume at some point they will be hacked, but when it happens, I want to detect and accommodate. And the same thing, of course, for faults. So uncertainty is making this more difficult because it is making the detection step more difficult. So as you may know, you need to compute a threshold that is taking into account the worst case of uncertainty. Otherwise, you have false positives. But uncertainty can also be nice if we can control it and we can add it on this channel. So between the data of our system and the attacker that is using this data to build an attack. So in this case, uncertainty is good. So we have these two facets. On one side, uncertainty that is physical, we call it intrinsic, is bad, makes our job more difficult. On the other side, extrinsic uncertainty that we can add on the cyber layer can be good because it will make the life of the attacker more difficult. So then let us look at these two facets and start with the first one, fighting uncertainty in the physical world and why it makes our job more difficult. So the usual path for reaching fault tolerance is, as I was hinting to, is to detect a fault, isolate it, and accommodate it. And well, if you're interested in seeing all these kind of events in the movie industry, so I found out that there is a series called Mars from National Geographic. And the first episode, they actually have a few minutes where they are actually doing this. And that's amazing, because if you're a computer scientist, maybe you get covered in movies. So there are always computer scientists, mad physicists, but control engineers working on fault tolerance, they don't get so much screen time. So this is one of the few things I found. Okay, so the kind of approach I'm using for detection is the model-based. In the model-based, you assume that you have your plant, you can take measurements, and you have two blocks here, one to generate a residual, one to generate a threshold, and then you do a test here. And if the residual is, let's say, crossing the threshold, you raise an alarm. When you have a dynamical system, a popular way of doing that is through an observer. So you're taking measurements, you build your observer based on some nominal model, and the residual is the estimation error of the observer. In general, the residual is the difference between two, what we say, analytical redundancy relations. So different ways of computing the same thing. And the threshold is some maximum allowed value of the residual in healthy conditions. So the physiological maximum value of the residual. So the problem is that the uncertainty is the reason why we need a threshold in the first place. And also it means that we have a higher uncertainty, we need to make the threshold higher. And so if your fault is small, as it's causing a small residual, you're not detecting it. So some questions about how to do that, maybe they are boring, so we'll not go too much in details. But one way to formulate it is assuming that you have a discrete time system. You have some nominal dynamics here, f. This is a function of x and u, but it also depends on another signal that represents the uncertainty and another one that represents the fault. And you have measurements of the state of the system that are anyway affected by measurement noise. So you have two ways uncertainty is entering the system. You can build your observer, for instance, a simple one-burger one. And then, just by taking this equation, you can compute what is the dynamics of the residual. So the residual ends up being a dynamical function of the previous value of the residual and one total uncertainty term that we call delta. And delta is a shorthand for all the possible ways uncertainty is causing the model to be different from the function. So for instance, the fact that we have the measurement noise, but also the fact that when we apply the model, we are applying it to measurements that are affected by noise itself. So one way to visualize that is like saying, okay, I have this function sigma that represents the way the residual is generated. And so we start with a current value of the residual, which we know because we measure it. And then we have all the possible values of the uncertainty that causes all the possible values of the residual at the next time step. So if you do this, when you assume the system is healthy, you can compute the set of all the possible values the residual can take. And then one natural way of building the threshold would be to box it. So you compute a box containing this set. And this makes sense. But this box has one nice property and one not so nice property. The nice property is that by construction, you don't get false alarms. But you can get missed alarms, because if your fault is causing the residual to end up here, outside this set, but inside the box, you don't detect it. So can we do better than this? And then let us try to define what is better. So what is a good detector? So forget about faults for a while, and we focus on detecting cats. So this is what Google is made to. When you have the photo of a dog and your detector says it is not a cat, well, that's okay. This is a true negative. When you have a cat and it says cat, this is a true positive. And then, of course, you have the other two possibilities, a false positive and a false negative. So one popular way of describing how good is your detector is to build a ROC curve. So you take a lot of pairs of these images and combinations, and you let vary some tunable parameter of your detector, like the threshold value. And you look how many false positives you have and how many true positives. So usually good detectors are in this zone. This is the ideal perfect detector. And then if you have some very bad detector, they will end up in one of. For instance, this is detector that is always saying cat. And the interesting thing is that it has a true positive rate of 1. So from that point of view, it's perfect. But of course, from the other point of view, it's not, because the false positive rate is also. But as we were discussing this morning, this is probably not the best way, because you also want to take into account the effect of the false. So detecting a cat is one thing, but detecting a dangerous cat is more important. So as we were discussing this morning, the ROC alone probably is not the best way. Okay, so how can we improve then on our threshold generation problem? So we were looking at several approaches to generate the threshold. So if you look at that as a set, so visually to make things easier, one possible way to generate a threshold is to consider the norm of your residual and construct a threshold on the norm, which is like saying you have a ball constraining your healthy residual. Or another approach is to take every single component of your residual and box them in the box. And then slightly more interesting is to use an ellipsoid to boundaries or then a polygon. But all these approaches still have some empty space where you can get missed detection. So our idea is, let's try to make it fit as tight as possible. So switch to some arbitrary shape for the threshold, and also try to make it less conservative by taking in some possibility of false positive, but in return, we get a better detection. So the idea is that if we can determine whether some samples are very rare, we just don't take care of them. So we let them stay outside. So in black, I'm denoting samples, possible samples of the healthy residual that are common. And this white one is something that is really uncommon. So I can just drop that out of my threshold. I will lose a little tiny robustness, but I get better detectability. And so this is the idea. And the way we solve that is to introduce a chance constraint formulation. So we an optimal problem where first we define a threshold set that is probabilistically alpha robust. So we determine a probability that is acceptable for us that the threshold is robust. So robust means that if you have a healthy residual, it will be inside or outside the set. So you want it to be inside the sample probability, or otherwise you want to limit the probability that it's outside. It is the same. And then we introduce a parameterization for the threshold set by defining it as the C superlevel set of some function, which is like saying you have a function defining a surface like a mountain, and you cut that with a plane at a given height that is equal to C in this case. The shape that you get is the shape of your set. And this indicator function, generalized indicator function, is not any function, but is some class of function that is parameterized by some vector theta. And we use polynomials, for instance. At this point, we can define the optimal threshold problem as we want to minimize the volume of the threshold set, because the smaller, the better from a detection point of view, such that the violation probability is less than something that is acceptable. One problem is that this is a chance constraint problem, so you don't have a way to solve it in general. So we switch to a numerically tractable approximation of that using the scenario approach. So we replace the probabilistic constraint with samples of that, which in our case means to draw a random sample of the residual and add a constraint saying it should be inside your set. Now, the intuition is that when we do this for a finite number of samples, the chance that that rare value of the residual is inside here is very low. So most of the time you don't see that. And indeed, the threshold that you get as a solution of your problem is this blue one. Now, one interesting question is how many samples we need to generate for this constraint. There is a theorem that we actually described in this paper here in ACC 2017. This theorem tells you that the number of samples that you need is linked to the probability alpha that you have here, and another probability that is beta, that is the confidence that you have in this solution. So the tricky part is that the numerically tractable version here, the sample constraint, is solving the original chance constraint with some probability itself. So this is the confidence. The solution we get here is a solution of this, and we describe it as this. So you have some formula that basically tells you the higher the confidence or the higher the degrees of freedom in the parameters here, the higher the number of samples that you need to generate. So this is wonderful because it holds whatever is the distribution of the residuals that we have, but in practice is quite conservative. Okay, so we tested this on an example, the classical 3 times system, and no, doesn't work. Okay, sorry. Well, there should have been an animation, but don't worry. So this is the kind of sets that you get when you apply it to a 3 times system where you have basically 3 dimensions. So the little dots that you see here are all the samples, and these kind of sausages are the sets that we got using a 4th order polynomial. And then we tested it with some simple fault, I guess a leakage in one of the tank, and check what is the volume of this set with respect to a deterministic one, a box one. And the thing that we realize is that, as expected, this ratio is less than 1. So our volume is smaller than the one you get in the deterministic set. Almost always, and anyway, always before the fault. The fault is happening at 20 seconds in this case. Okay, that was the. All right, so to which kind of systems do we apply these ideas? One kind of system we are working on in our group are wind turbines. So we have a lot of research going on that. Wind turbines are extremely popular. Everybody says that they are the most promising way of generating renewable energy, especially if you put them offshore. But the thing is that if you put them offshore, then the environment is quite harsh. It is also quite costly to go there with a boat to do maintenance. So it's very important to detect failures and degradation soon enough in order to plan for maintenance in an optimum. So one kind of faults that can occur in turbines is a fault to the pitch actuator. So to explain that, please consider the picture of the turbine, and the 3 individual blades, they can rotate this way. And by rotating, because of the shape of the blade, you can control the amount of thrust that every blade is generating. So if you want your turbine to spin faster, you control the pitch to some value, and it will start rotating faster. If you want to keep steady state, then you rotate it the other way, and then the pitch is such that the thrust generated is small. Okay, the problem is that these actuators can fail. And so we developed a way to detect this and to accommodate as much as possible. And also taking into account that on turbines, we have sensors of the moment to each blade. So when wind is flowing, the blades will bend a little bit. So for each blade, we have a sensor measuring how much they bend. So how much is the moment generated by the wind. So the approach that we are using is to combine 2 things. Subspace predictive repetitive controller that is accounting for slow phenomena that are occurring on a long horizon. So we have 2 blocks here, an identification block and a predictive control. So the identification block is constantly identifying the plant. So if you have a long-term variation, you can accommodate. And then you redesign the controller using this information. But the problem is when you have a fault on the pitch, this is an abrupt fault. So this will be too slow to adapt, and you risk your turbine to break down. Because when only one actuator is stuck, then you start to have unbalances in the rotor, and it can destroy. So we have a fault diagnosis block that will detect it and then command switching an abrupt change in the parameters of the controller that we can pre-compute offline. So this is an example from some simulations that we have done in the case of an abrupt fault to this blade. And maybe you can see it's quite small, but the red line is our architecture, and this is the moment. So you can see that we have much less oscillations here with respect to the other methods that are very slow, and so the turbine is still operating with a rotor unbalanced. Another example is maybe closer to what you are doing. It is about detecting attacks in cooperative autonomous vehicles. So we are assuming here that we have several autonomous vehicles that are platooning. So they want to drive following each other at a given distance to save fuel and to be more efficient. And every car has a radar in front to measure distance and relative velocity with respect to the one that is following. But for guaranteeing some property that's called string stability, you need also to have wireless communication from the car in front to the car to the back. Basically, the car in the front is telling the other one about the acceleration, the intended acceleration. So you have delta position, delta velocity, and acceleration, but acceleration is transmitted, not measured. So what happens if we have somebody that is injecting false data on this channel? So if you look at the control law that is implemented by this car, well, you get this equation. This is called cooperative adaptive cruise control. So this is quite a common way of solving this problem. And in this equation, basically what you have, the derivative of the intended acceleration of the car in the back is one term here for stability, then a proportional and a derivative term that depends on the error in the position and the relative velocity here. So this is measured, plus one term proportional to the acceleration of the car in the front, which means that when you are with zero delta velocity and at the right delta position, when the car in the front is accelerating, you are also copying that acceleration. The attacker is injecting an extra signal in the intended acceleration that is communicated here. What we did here is to use a slightly different kind of observer, a sliding mode observer, which in general is written like that. So you need to do a change of variables, and you end up with a set of variables that are affected by the estimation error, and a set of variables that are not. And instead of having the proportional feedback term that you have in the Leuenberger or Kalman filter, we have this term here that is switching. So this is how the sliding mode observer works. So it is related to the sign of the error. So when sign is positive, you're driving down the estimation error, and the other way.
So can you avoid the sign function?
Well, there are higher order version of that are avoiding that. So we use the simple vanilla version of that, and we have the sign. But anyway, one interesting thing is that this switching term is entering the equation through the same channel as the attack. And so you can prove that if you filter, low pass filter the switching term, then you get an estimation of the attack. So we did some simulation, and we were assuming a scenario where the green line is the intended acceleration of the car in the front. So you have a positive step in acceleration and a negative. And then the attacker is adding on top of that this other step. So the acceleration that the car in the front receives basically has two steps. And the point is that the attacker is trying to make the car in the back to crash into the car in the front, because the one in the back thinks that the acceleration is higher than what actually is. So we tested this scheme in some more realistic case where you have event trigger communication. So you have communication from the car in the front when the velocity of the car in the front is changing. Otherwise, you have it anyway, but with a low frequency. And so we tested our scheme, and the blue line is the estimation. The red one is the true attack, and indeed, it is converging to the true value of it. You see that you have some spikes in the estimation here. They occur when you have a change in the intended acceleration of the current flow. But this happens because of the event-triggered scheme. So at this moment, you don't have communication from the car in the front until sometimes later. So during that time, you initially estimate something like an attack. But the smart thing is that when we compute the threshold, we take that into account. So we know that if we don't have the communication, it's like having higher uncertainty. So the threshold is growing. And so we don't have false detection here, but we have detection at that point when indeed we were under attack. And then we applied this idea also to other similar problems, like in an intersection crossing, when you have autonomous vehicles that wants to go to an intersection without a traffic. And then the next step would be to test this in practice. So we are building some experimental small scale car. So we are using a normal RC car with a sort of Arduino, Raspberry Pi board on that for low-level controller, and a stereo camera, and an NVIDIA board for vision. And that's implementing the radar. So instead of a real radar, we have a stereo camera. And I don't know if you can see that, but we have some LED matrices on the cars in order to do some communication, but visual communication using LED matrices. But anyway, that's still in the matrix. Okay, that was the first part. One thing, if you have questions, please ask. So you are free.
So I don't get how you do the vision-based communication.
Oh, yeah. So the idea
in the experiment.
The idea is that every car has a camera here, but also
so many directions.
It looks only front,
okay.
But we also have LED matrices on the front, the sides, and the back. Mm-hmm. So the car in the front sees the LED matrix on the back of the other, and we can communicate the acceleration using that. But this is, let's say, far-fetched. The first step would be just to use that. Okay, that was the first chapter. So some classical results about fault diagnosis and fault tolerant control. Anyway, situation where we don't want uncertainty. It is already there, but we don't want it. Now, this second part is about a situation where we want to promote uncertainty, not for us, but for the attacker. So let's go back then to the situation. We are now looking at how attacks can compromise security and cause then a loss of safety or resiliency on the physical. So when we talk about security, probably you have heard many times about security triads, but today I'm presenting to you a triad of triads, so a sort of meta triad for security. So the first triad you know about is the one about confidentiality, integrity, and availability. That's what people in computer science in IT. But the dual of this one is about mechanism an attacker can use to compromise this. So disclosure attacks compromise confidentiality, deception, integrity, disruption, availability. And then the last triad is about methods that we have to mitigate attacks. So we can use methods to detect, which is what I was showing in the first part today. You can have methods that improve the resilience of your system, make it work even under attack, or you can prevent an attack, for instance, by using normal IT security. And now, short commercial, sorry. So if you are more interested about that, together with Andre, so we edited and co-authored a book about the topics, and the content of the chapters that we have is spread like these among all these different subtopics on security. But sorry for that, let's stop. I will now talk to you about 3 different mitigation approaches that I have been working on. And one is about differential privacy, watermarking, and just some hint about homomorphic encryption. And I will start with privacy. I guess many of you already know about differential privacy. I will anyway repeat some of the key concepts. So differential privacy was born in the computer science world. So one of the things they start defining is a query. So a query anyway is a function that is providing you information about some knowledge that is contained in a database. And there are databases that have some particular property of being adjacent. So two adjacent database will differ by only one record. Or you can have also more general definitions of adjacency based on norm. So for instance, in this example, when we have these characters from tools, so smart fact, smart, and I don't know the name of the other one, two adjacent databases could be the one containing 1, 2, 3, and the one containing 1 small fact and 3. So maybe what you want to keep private is the presence of small fact in the database. But the bad guy actually is asking a query in order to try to understand whether small fact is part of the database. So the idea of differential privacy is not to directly answer queries by possibly malicious third parties, but to have in between a curator, somebody that is filtering the result of the query and applying to that what we call a mechanism. And then communicating back to the third party the result of the mechanism, not the raw result of the query. The way to define the mechanism is to first look anyway at the sensitivity of the query. So you want to know how much the response of the query depends on the fact that the private data is in the database or not. Because if the answer of the query is anyway the same, if this is or not in the database, then you can just communicate. If instead the query result clearly tells you it is or it is not in the database, then you don't want to provide this result directly to the third party. You want to add something to hide. So the idea of differential privacy is to define such privacy preserving mechanism from a probabilistic point of view. And the idea is this mechanism is some randomized function. So we talk about probability. And for different possible answer that the curator is giving, we try to do a test. So this bad guy ideally can do a test. And the test is the answer belonging to some set? So the thing is, if a query and then a mechanism provides an answer when Smurfette is in the database that is inside the same set, that is when Smurfette is not present. From this point of view, you can't detect whether the private data is there or not, because anyway, the mechanism, the result, will stay in that state anyway. But this is defined in probabilistic terms. And so you compute the probability that the result of the mechanism is inside a test set when you have a database with the private data, and should be less or equal to an exponential function of the probability when it is not, and the other way around. So visually, it's like saying I have the answer when private data is there, should stay inside some bounds, plus and minus. So the higher these bounds, the farther away, more confusing for the attacker is the mechanism. So how we implement this mechanism? In practice, it can be as simple as adding noise to the query. And the Laplacian mechanism is actually one way of doing that. So you you generate samples from the Laplacian distribution with variance that is inversely proportional to the sensitivity. And this way, you can make this noise large enough to cover the private data, but not more than. So we tested this for an example where we are imagining that we have tanks and pipes. So that can be interesting. So all the nodes in this graph are tanks, and the edges represent pipes. And you have two systems. The first one has private information. The second one is the one that can try to recover this private. And the private information is whether you're using this pipe number 1 or the pipe number 2 to provide water to these tanks. So it is like saying you have two different sources of water, and maybe this can lead to different prices for end customers, but you don't want to let others know which one you are using because you want your policy for pricing. You don't want others to try to understand it. So how can another one try to understand anyway which water source you're using? Well, they can try to do some fault detection on that. So use an estimator that has a model of this first network, and then try to check one of the two possible hypotheses, whether this route is used or this other route is used. So we made some simulation where we assume that during an initial period we are using the first route and then the second route without problems. And so if the second system is trying to compute an hypothesis testing of that, it will end up that it's pretty easy for them to understand I was using the first one and then the second one, because you can compute a residual signal that is very sensitive. But in the second case where I am adding privacy, so the blue signal with all the noise is the privatized one, then if you look at the residual from the point of view of the third party, well, that's noisy at a point that you can't define a threshold to differentiate one hypothesis from the other. But this actually points out one key problem in differential privacy in general, which is the utility privacy trade-off. So this is an example where privacy is attained, but at the expense of possibly utility. Because if the other party takes data to do something useful, in this case, it is prevented to do so. So in general, if we have both to protect privacy and do something with the data, we need to take that into consideration and look at ways to reach the best privacy utility trade. So to investigate this, we consider another example where we have these two actors communicating, but this time, the second one really needs information from the first one in order to do something. And in our example, this something was estimation and a full diagnosis of its own system. So let's make again the example of water and pipes. You have two utility providers, they own part of the network, and they need to locate leaks in the pipes. And the second one needs to know what is the level of the tanks of the first one, because otherwise the models the second one is used can't be used. This is a possible example. Or electric energy sector. Well, in this case, we defined a residual as the Malanovis distance of the estimation error of some observer that is implemented. And under the assumption that we had there, so linear systems, Gaussian noise, it turns out we can use a chi-squared detector. So we define the threshold as the inverse tail of the chi-squared distribution for some desired false positive rate. And then we look at one interesting quantity, which is, we call it the signal noise ratio. And it is some way the effect of the fault divided by the covariance of the noise, the uncertainty that normally you have. So if you are in this simplified setting, then it is easy to compute the true positive rate, looking at the tail again of the chi-square distribution, but the non-center one. And this is a function of the threshold and the signal to noise ratio. So this is the usual thing that we have in fault detection. So more noise means worse true positive. Now, what happens anyway when we have privacy? And we want to look at what happens in terms of this true positive rate and the robustness so the false positive. So we use again rock curves, the one that we introduced before, and we consider two cases. The first case is Alice is honest and open with Bob about the fact that she's using differential privacy. So Bob knows that there is additional noise on the data he is receiving. If Bob knows that, he can compute a new signal to noise ratio and can still have the same false positive rate as the one that he wanted to have, and a true positive rate that is decreasing as a function of the amount of privacy. So the more privacy you have, the more you are moving into this zone. So your true positive is worse, but at least your false positive rate is still the same. Because basically Bob can account for the additional noise. But if Alice is not open and honest and Bob doesn't know about the extra noise due to the differential privacy mechanism, things become very weird, because now the operating point on the rock curve, they are not on a single line as before, they are moving around. And you see that some way strangely beta, so the true positive is better, but the false positive is getting quite worse. So instead of it being a false positive rate of 5%, as it was the design goal of Bob, it can get as high as 1%. So we get closer to the always cat detect. And so here again, is privacy always ethical? Because from the point of view of Alice, it is an advantage. But for third parties, can be a disadvantage. So maybe when designing these kind of schemes, we also need to try to answer this question. Okay, I guess I have still 15 minutes. All right. Okay, so we talk now about another topic, which is watermarking. And this research that I made together with Andre is motivated by some kind of attacks like replay attacks, stealthy attacks, rerouting attacks. And so I will show now something about replay attacks. So you probably already know that they are based on taking data from sensor, and the attacker, so the pink part in this case, is replacing live data with recording of previous data. So if you want to assault a bank, you replace the CCTV footage with some that you recorded previously. When you apply this to a control system, something quite nasty in a way happens. Because if you look at the feedback loop during a replay attack, it is open. Because when you are using recorded data, then the loop is no longer closed. So if you have an unstable plant, it is going to explode. And this is very bad also because replay attack, if timed properly, they are undetectable if you use normal model-based detectors. So our idea was to add watermarks. So you know about watermarks in images, so they are additive. In other kind of data, one-dimensional data like audio data, or could be signals from a control system, it is more popular to distort the signal to apply a filter. And this is called multiplicative watermarking. So what we did is to implement watermarking to the sensor data. So we have data coming from the plant, we filter it here, we add some distortion that we know, and this is the kind of data sent to the network and which is subjected to be repaired. On the other side, the received data is first de-watermarked, such that in nominal condition, you get the normal performances, because this is applying and this is perfectly removing the water. And then this is going to the controller and to a detector. And this is possibly one advantage with respect to other noise-based additive watermark mechanisms, because we are not diminishing the performance of the control loop. And also, when your signal is small, our watermark is not so obvious. So an attacker can't easily spot this because it is multiplicative. So when the signal is small, the watermark is small. And we applied this to an example. a linear system 2 by 2, which is unstable. So during an attack, what happens? We have the control loop, feedback loop is open here. So we have the recording is like a virtual plant and controller that are producing all measurements. But the thing is, in our scheme, the real data is watermarked here. And the key point is that the watermark is parameterized. And these parameters switch over time. So for 10 seconds, we are using one watermark. For 10 seconds, we are using another one. So at some point, we are using the watermark number I here. On the other side, we are removing the watermark number I. We expect that to be present in data. But in reality, the attacker is using an old one, possibly that was watermarked with a parameter number J. So the thing is that now we have data that was watermarked with number J that goes to the watermark remover number I. And we designed the thing in a way that when you do it, it is very easy for the detector to detect them. So there is quite a mismatch between different watermarks. And this is a simulation example. We were assuming to have a square wave a reference that is followed by the system. We apply a first watermark at time 0, a second one at about 100, and the third one at about 225. The attacker is recording data at 100 and something, and replaying that after 200 and something. So data that is replayed here has watermark number 2 on that. So during this period of time, the watermark remover is also expecting watermark number 2. So when it removes it, the residual of this detector stays small. So the residuals are these. But when we switch watermark and the remover is removing watermark number 3, this is inducing this big mismatch, and the detector is immediately detecting it because the residual is crossing its threshold. So the same thing can apply to the case of stealthy zero dynamics attacks and rerouting. So then final thing we are working on this topic is implementing fully homomorphic encryption. So we're not doing here anything new from a theoretical point of view, but we want to implement in practice this kind of scheme. So just a very brief introduction. So fully homomorphic encryption is such that when you apply this a sort of equivalent sum to encrypt data, you get the encrypted value of the sum of the arguments. When you apply an equivalent multiplication to the encrypted data, you get the encrypted value of the multiplication of the two arguments. So this is interesting because in a normal encrypted control scheme, you have from the plant to encrypt sensor data. The controller side, decrypt, apply the control law, encrypt the result, decrypt it again, and apply. So you have a lot of overhead, which is not good for a control system. You don't want time. With homomorphic encryption, we apply only encryption here and decryption here, but the controller is working on encrypted data. The problem is that it is very computationally expensive. So we are trying to implement this, the plant and the two encryption schemes, and the controller on two different FPGAs in order to have it in real time. And the interesting thing is, if you look back at this dichotomy between good and bad uncertainty, in this case, it is like we are adding a sort of infinite uncertainty, because from the point of view of the attacker, at least this is what I was believing. From the point of view of the attacker, this encrypted data is like white noise. So it's like you are adding a lot of it. But somebody this morning was telling me that actually you can do nasty thing with you were telling me. So an attacker can still use full homomorphic encrypted data to create an attack. So probably some very interesting development on this, of course. Okay, so I won't go too much into details. So we are almost at the end of the talk. So that's time for some conclusions, related problems, and future. So this is what we were talking about today. The different kind of uncertainty, something present in the physical world, something that can be negative or positive depending on the role that you have. So if you are the defender, this kind of uncertainty is good. Other situations where you encounter uncertainty, things we are working on. So one problem we are working on with Volvo is how to train some algorithms they have for predicting residual useful life of batteries. And you need data from operation of these batteries in order to tune the parameters of these algorithms. But the issue is that their data is like a piece of cheese. There is a lot of holes in that. So this data is sparse. It's like having a lot of uncertainty about what's happening here inside the code. So what we are trying to do in this project is, well, very simple, I think, yeah, is to use first principles, so models of the dynamics of the battery, to try to fill some of these holes. But the problem is that first principle models themselves have some parameter that you need to estimate. And we have only this data to estimate. So again, how we can estimate these parameters with data that is full of holes. So that's the problem we're working. And then we are working on a different kind of approach to deal with uncertainty for robotic manipulation applications. And we are using a concept that is called active inference. So in active inference, they are trying to mimic some mechanism that is thought to be happening in our brain about we adapt and we control. So inside the controller, there is a sort of model about the robot that is defined in terms of beliefs on the internal state of the robot. So this is a probabilistic formulation of the robot. And you have some knowledge about how this belief will turn out into real sensory experiences. So I know that if I move this way my hand, I will hit the table. So I am expecting this sensation. When you have real data coming in, you're using this real sensation and you're inverting this model to update your beliefs. So this is a sort of observer. But then to generate the control actions, you try to generate the actions that will make your belief reach some goal, even if you don't have a precise model of the system. And this turns out to be working quite well. So we were applying that to a manipulator that needs to grasp a bottle. We don't know if it is empty or full. And we compare the adaptive active inference controller with a model reference adaptive. And one thing that we found is that motion in this case is much smoother, but most of all, it is really easy to tune that controller because with active inference controller, you have just a few parameters. And with this one, you have tens of parameters. So this is something we are doing together with the cognitive robotics department in our faculty, Oxford Robotics, and with funding from a Dutch company that wants to put robots in supermarkets to fill the shelves. And then one final slide that is actually the less developed, but the thing I like most. Let's put it this way. So we were talking about uncertainty today. And a lot of algorithms that we presented are based on the assumption that we can do uncertainty propagation. So we know what are uncertainties in measurements and model, and then we propagate them through our dynamics, our residual generator, for instance, and we use that to design the threshold. Or we do a similar thing for computing sensitivity that is needed for differential privacy. So we are taking that for granted, but the question is, can we always do uncertainty propagation in an efficient way? So can we do that for arbitrary nonlinear models? And that's the good thing to answer. So there are different ways of doing uncertainty propagation. So assuming that we have a car and we want to estimate what is the trajectory of the car over a time window in the future, the simplest way of doing it is the deterministic one. So you compute the nominal trajectory and you add some bounds around it. Or you can use a Kalman fit, Kalman predictor. And in this case, if you think about that, actually, it's like taking the nominal trajectory and then adding ellipsoids around that. And the dimension and orientation of these ellipsoids depends on the covariance matrix. Other approaches are polynomial cows, which are doing a sort of Fourier expansion of the PDF of the trajectory, or using a Gaussian process where data is used to compute the future covariance, or you are using a particle filter when you propagate forward in time particle representing possible states of your system. But in order to make that computational feasible, at some point, you need to kill particles. Otherwise, they will grow out exponentially. So the ones that are unlikely, they are killed. Now, the problem is maybe the one that was unlikely was containing some important information if you have a critical system. So can we try to propagate everything forward? So the idea I'm working on is to implement that as a sort of finite element model where the thing that is moving is the probability mass of the system. And this amounts to solving what is called the Fokker-Planck-Kolmogorov equation, which is a partial differential equation whose solution is the PDF of a stochastic differential equation. So this is your dynamical system with uncertainty, and this is the equation solving for the PDF of that. And as this is a partial differential equation, you have numerical ways of solving that as people solve electromagnetism or computational dynamics. And that was it. So thank you.
Thank you very much for the very interesting presentation from Riccardo. Now we'll take a very quick question from the audience, considering by time.
Can I ask?
Yeah, sure.
Regarding this multiplicative watermarking, so did you an implementation aspect that needs to synchronize the modulator and demodulator? So